Hello physics students, welcome to episode 5, Satellites and Kepler's Laws. We've already learned a little bit about satellite motion and its relationship to gravity, and so we've combined circular motion with gravity to give us satellite motion. And we can explore that a little bit more. There's our equation for gravity, there's our equation for circular motion, and they're all equal to each other for satellite motion. And so we can get rid of that, rearrange this, add in the fact that the velocity is 2 pi r over the period of one rotation, and we get this, and that can be rearranged in a variety of ways, and this is one of the ways of rearranging it. You can of course have r as the subject and swap everything around as well, or r cubed to be more precise. And you can get this ratio here. Now notice that this ratio is interesting because it's the ratio of the radius of orbit to the period, and effectively this side of the equation is a constant, and we'll talk about that shortly. Now that's on your formula sheet, and we can note also that there's no mass. Now quick little change there, not yet. There's no mass of the satellite, so it's independent of the mass of the satellite. And that tells us a few things, this arrangement. It tells us that the ratio r cubed divided by t squared is a constant for any mass orbiting a larger mass, and this is effectively Kepler's third law. And it works for any satellite motion, be it the moon around the Earth, electrons or spiral galaxies. For example, if we have this ratio for one satellite, let's say Earth. Earth is a satellite of the Sun. If we looked at another satellite, Venus, in the same solar system, the ratio would be the same. And it works for the same system. It doesn't work out for different systems, but only for the same system, because this is effectively a constant for each system. It can be rearranged to give you this mathematical arrangement, which is just this. 6 of one, half a dozen of the other. Now, this one, that's the one given on your formula sheet. Okay. Now, the Kepler's law. Kepler was around from 1571 to 1630. He looked like that. He made some significant discoveries. Newton later showed that Kepler's law could be derived mathematically. He derived them by observation, effectively, and he made some major discoveries, and he was so significant that they actually named a space telescope after him, the Kepler Space Telescope, which is, I think, just about to be decommissioned. It was photographing or imaging planets around stars, and it found thousands of them. Now, Kepler's first law states that the path of each planet around the Sun is an eclipse, with the Sun at one focus. Now, we've been lying to you. Oh, shock horror. We've been saying, or haven't been explicit in it, but we've been saying that circular motion, the Earth going around the Sun, is an example of circular motion. Well, strictly speaking, the Earth doesn't go around in a circle, it goes around in an ellipse. What is an ellipse? An ellipse is a sort of flattened circle. Mathematically, it makes, for what we're doing, it makes very little difference. Okay, if you're working for NASA, you'd have to take some consideration into it. And this is extremely exaggerated. The orbit of the Earth and most of the planets in the solar system are near circles, and the Sun is nearly at the center of the eclipses. This is exaggerated, and this would give you the impression that the Earth gets very close to the Sun and then very far away from the Sun. That's not the case, and that's not the reason we have, for example, the seasons. Common misconception. It would, however, describe the motion of things like comets, which go a long way away from the Sun and then come back in and get very close to the Sun. But they're different sort of kettle of fish. Now, Kepler's second law relates the planet's speed to the distance from the Sun. Basically, you can pause this and read all this. Basically, it's saying that for something like a comet, when it's a long way away from the center of its focus, it travels slowly. And then as it comes closer and closer to the object it's orbiting around, it gets faster and faster. And so in this example, the going from A to B would take as much time as going from C to D. And so clearly the velocity here is less than the velocity here. And that was Kepler's second law. And I forgot to mention that Kepler was really important because before Kepler, everyone was believing that all the celestial bodies were in perfect circles. And he was able to explain that they weren't perfect circles and that things, depending on their orbits, were more extreme than others. And so things like comets would disappear and reappear, whereas things like Mars and Venus would their motion in the sky could be explained by the elliptical nature of their orbits, and Earth's as well. Kepler's third law states that within a system, this is the one we were talking about, you have a constant ratio of t squared on r squared, or the reverse if you like, and that's constant for each system that we're talking about. For example, every 36 years, Halley's Comet passes quite close to the Earth. At its most distant point in its orbit is much further from the Sun even than Pluto, so it goes way out there. Is the comet moving faster when it is closer to Earth or closer to Pluto? And according to the second law, it is moving faster when it's closer than when it is further away. So it's moving fastest when it's near Earth. Okay, that's just a summary of it. Again, you can pause it, saying the same things. Now for satellite motion, we of course have the centripetal force is equal to the force due to gravity. We can put these two equations together, which is what we did before, but we could do something different. We can actually cancel out the radiuses and get rid of the radius square, so we're left with 1r. We can cancel out the masses of the satellite, and we rearrange it, and we get v squared equals g m on r, which we can then redefine into this equation here, which is very important because that gives us the velocity. If we're given a satellite and we're given the mass that it's orbiting around and its radius, we can work out its velocity. For example, what is the orbital velocity required by a satellite at the altitude of 600 kilometers, which is where the Hubble Space Telescope sits, or 40,000 kilometers, which is where your typical communication satellite sits. Now for the close one, it's travelling quite fast, 7,550 meters per second. For the next altitude, it can travel slower because it's at a higher altitude. Its period, however, will be very much different because remember that the ratio of their periods and radiuses is a constant for the system. Okay, and this relates to that. In the next video, we're going to learn about the different types of satellites you might encounter in the physics course and the real world, and we're also going to quickly talk about space junk. Cheerio!